Hey everyone, and welcome. So today, we're going to get our hands dirty. We're moving past those simple, high-level APIs and really digging in. We're going from the blueprint all the way up to the skyscraper, building a custom PyTorch training loop from scratch so we can truly understand what's happening under the hood.
Have you ever just typed trainer.train and wondered, what's actually going on in there? What's the magic? Well, it's time to take off the training wheels and find out. Let's dive in.
So you might be thinking, why even bother with all this? And that's a fair question. The answer is really simple. It's all about control and flexibility. Building your own loop gives you the power to plug in custom logic, makes debugging way easier, and helps you really truly master the entire training process. And you can see the difference right here. On one side, you've got the trainer API. It's just one simple command, trainer.train. It's powerful, for sure, but it hides all the complexity. It's kind of like a black box. But on the other side, well, that's what we're here to do. We're going to build out every single one of those steps, and that's where the real understanding begins.
Okay, so just like any good skyscraper, we need a solid foundation. Before we can even start writing the loop itself, we've got to get our data, our model, and our optimizer all set up and ready to go.
We're going to tackle this foundation in 3 key steps. First, we'll post-process our datasets. Then, second, we'll create the data loaders. These are what will actually feed the data to our model. And finally, we'll set up the model itself and the optimizer that's going to do all the heavy lifting and learning.
First things first, we need to do a little bit of data cleanup that the trainer normally just handles for us automatically. We'll get rid of any columns the model isn't expecting. We'll rename the label column to labels with an S at the end because that's what the model is looking for. And finally, we'll set the dataset format to return PyTorch tensors instead of plain old Python lists.
So with our data all nice and clean, we can finally create our data loaders. You could think of these like conveyor belts for our model, serving up the data in shuffled, easy-to-manage batches for both training and later for evaluation.
Next up, the model. We'll load it up just like we normally would. But here's a really cool feature of Hugging Face models that saves us a ton of work. If you give it labels along with your inputs, the model automatically calculates and returns the loss for you. It's super convenient.
Now, to actually update our model's weights based on that loss, we need an optimizer. We're using AdamW, which is the default in the trainer. It's basically the Adam optimizer, but it has a much smarter way of handling weight decay, which helps prevent our model from overfitting. Honestly, it's pretty much the go-to choice for training modern transformer models.
And hey, if you want to level up your optimization game, here are a few pro tips. A weight decay of 0.01 is usually a great place to start. If you're dealing with absolutely massive models, memory-efficient optimizers like 8-bit Adam can be a total lifesaver. And just remember, for those bigger models, you'll often get much better results with slightly lower learning rates. All right, the very last piece of our setup puzzle is the learning rate scheduler. This little component's job is to gradually adjust the learning rate as we train. For this, we'll just use a simple linear scheduler that takes our starting learning rate and slowly decays it all the way down to 0 by the end of training.
Okay, the foundation is laid. All our pieces are in place. Now it is time to build the core engine of our entire script, the training loop itself. Let's do it.
This right here is the heart of the whole operation. For every single batch of data, we first push it to our device, like a GPU. Then we do the forward pass to get the model's predictions and the loss. Next up, the super important backward pass. Loss.backward calculates all the gradients that tell us how to improve. Then optimizer.step uses those gradients to actually update the model's weights. And finally, we update our learning rate and call optimizer.0_grad to wipe the slate clean, ready for the next batch.
And you can make this core loop even better. You can add things like gradient clipping to keep your training stable, or use mixed precision for a serious speed boost on modern GPUs. You can even use a trick called gradient accumulation to simulate having bigger batch sizes, which is a total game changer if you're working with limited hardware. So once we've done some training, we've got to evaluate our model, right? The evaluation loop is pretty similar to the training loop, but with 2 key differences. First, we switch the model into evaluation mode with model.eval. Second, we wrap the whole loop in a torch.noGrab context. This tells Python not to calculate gradients, which saves a bunch of memory and computation. Then we can just feed our batches to a metric and compute the final score.
Okay, so we've built a fully functional training and evaluation script. That's awesome. But what if we want to scale it up? Let's see how we can supercharge this whole thing for distributed training using the Hugging Face Accelerate library.
This is a super common problem. You get your code working perfectly on one GPU, and then you realize you need to run it on, say, 8 GPUs, or maybe even TPUs. How do you do that without having to rewrite everything from scratch?
Well, the answer is accelerate. It's kind of magical. Look at this. Before you had all that manual two-device code for your model and your batches. Now, you just create an accelerator object, pass everything to its prepare method, and replace loss.backward with accelerator.backward. And that's it. Device placement just happens automatically. It's incredible.
So yeah, it really just boils down to these 3 simple changes. You instantiate the accelerator, you prepare your objects, and you use the accelerator's backward method instead of the one on the loss. With just those tiny tweaks, your script is now ready for distributed training on pretty much any hardware setup you can throw at it.
So now you can build and scale your own training loops. To finish things off, let's just quickly cover a few key best practices that'll help take your projects to a real production level.
First, don't just rely on accuracy. Make sure you're evaluating on a whole range of relevant metrics. Use powerful libraries like Optuna to systematically find the best hyperparameters for your model. Always track your metrics to see how things are going. And hey, when you've trained an awesome model, share it on the Hugging Face Hub so the whole community can benefit.
And that really brings us to the core takeaway of all of this. Building a manual loop means mastering one fundamental sequence: the forward pass, the backward pass, and the optimizer step, then zeroing out the gradients. Once you truly internalize that flow, you have complete and total control. You now have the skills to build a custom training pipeline from the ground up, to scale it for high-performance hardware, and to follow the best practices for production. You've officially peeked behind the curtain. So I guess the only question left is, what amazing thing are you going to build next?